Thanks very much for coming along. This is going to be a talk not so much about Agile, but a little bit about the interesting topic of machine learning, neural networks, and AI. What I'm hoping to do with this session is just to give you a feel for how neural networks actually work. So if that's something of interest, please stay. Otherwise, I won't be offended if you want to go to some of the other interesting talks around the place. We're not going to go deep into the maths or anything like that. The purpose here is for you to kind of understand, well, what is it that they can do? How is it that they work at some level of detail, so that when you go and kind of explore the topic yourselves, whether you want to explore some of the great tools out there like TensorFlow and PyTorch, you already know what it is that you're using. And it's useful to actually understand what they're doing, because as you know, tools in the wrong hands can sometimes go wrong. So I'm hoping that you leave with a little bit of an intuition. And to keep things exciting, I'm going to do a bit of a live demo at the end with a bit of audience participation. And if it goes wrong, I've just checked my exit is over there. Okay, right. So let's dive straight in and ask ourselves a couple of questions. I think that really illustrates the power of these new ways of computing. So if I ask my daughter, who's 9 now, if I said to her, can you point out the people in that photo? She could do that quite easily. And if I asked her to add up all those numbers, she wouldn't like doing that. She'd find it quite hard. She might make some mistakes. Whereas if I ask my computer, and I code it with Python or JavaScript, I can do that some really easily. But writing a program to kind of work out how many people there are and where they are in that photo is quite hard. And what this example does, it illustrates different problems which are easy for our minds, our brains to kind of solve compared to the traditional computing and traditional approaches to kind of solving problems. And we want to be able to do more of these kinds of things. We want to be able to do cool things like image recognition, voice recognition, playing games of chess, driving cars, and so on. So that's the journey we've been on over the last sort of 20, 30, 40 years, and it's really exciting. You can't have missed some of the stuff in the news, you know, self-driving cars, Google kind of playing, you know, really good games of chess and Go, which surprised a lot of people with how fast we were able to solve that. So it's a very exciting area. I mean, most people here will have smartphones, and those things are, you know, super advanced. I mean, I can talk to my smartphone, and it can generally understand what I mean, and that's amazing given how small it appears to be. Okay, so let's dive in, and what I'm going to do for the next few minutes is start with some really simple noddy examples, and they're so noddy they might bore you, but they will have some important points which are relevant to how machine learning and neural network works. So bear with us, and you'll benefit from some of those insights. So imagine we're trying to build this machine, this kind of AI, super-duper kind of mysterious, futuristic machine. We want to be able to ask it a question and get an answer from it. And in between those 2 points is doing some kind of thinking. That's a description in plain English. And if we use computing terms, we might say, well, give it an input, this machine, and we get an output, and it does some kind of calculating, some processing. That's the kind of the scheme we're working with. Let's imagine we've got a task, which we know is actually easy, but imagine it's hard. Imagine we want to convert kilometers to miles. Let's just pretend for a moment we don't know how to do that. We could come up with an idea, a theory, a proposition for how the two things are related and try it. So we could say, inside this machine, we're going to have a very simple calculation, which is 1 multiplied by a number gives us the answer. It's a linear relationship. We're just trying it. We don't really know. And we start with, well, where do we start? What's the factor that we multiply by? We don't know. So let's try something at random. Let's say a half. And it gives us an answer, you know, 100 miles. It tells us that it's 100 kilometers is 50 miles. It's not too bad. There's an error of about 12. It's not great. It's not too bad. Can we improve that? That's what you would do if you were using a pen and paper. Let's try another number, 0.6. That is much better. The error has reduced. This thing seems to be learning. Yes, it's a really noddy, trivial example, but the idea of seeing what the machine gave us as an answer and looking at how wrong it was and using that information to tweak something in the machine, this parameter in this case, that's the essence of machine learning. It's a grand term, but it's not so different from what we're doing in this very trivial example. Let's tweak it again. We've gone too far in the other direction, so we learn from that. This happens to be a much better estimate. So at its core, that is what machine learning is. Yes, we can have very sophisticated machines with very sophisticated models in. And I guess everyone's very happy with that. That's not too complicated. But there's some important points there. The points to take away are, when something appears to be more complicated that we can kind of understand how it really works, like how do brains work, we can come up with models and see if they're good enough, and we don't always know all aspects of that model, so we can put in parameters which we can tweak. And school children can have a go at doing this. It's not complicated. My daughter, who's 9, she can go into the garden and she can collect bugs, as she sometimes does. I imagine she's done this, and she's kind of measured them, their width and their height, and she plots a graph, a picture, and she might find, actually there's 2 clusters, and she might find that the caterpillars are thin and long, whereas the ladybirds are short and round. Now we can look at this and say, there definitely is. There are definitely 2 clusters, two types of insect. Maybe we can train our machine to do something more sophisticated than converting kilometers to miles. Maybe we can train it to recognize what bug it's seen, just ramping up the complexity a little bit. Now, when we were looking at that conversion between kilometers and miles, we had a very simple model, a linear model, where we multiplied one number to get another. If you remember from school maths, that's how lines are drawn, y equals gradient times x. And you think, okay, we could use that simple model, couldn't we? We could have a line which has a parameter, the slope, and we could try and train that machine to correctly separate those 2 classes of object, those 2 types of insect. This is not a good line because it doesn't successfully separate those 2 kinds of insects. This machine is now a classifying machine. That's also not a good one. It's a different line, but it doesn't separate the 2. And this one does. And when we take ourselves away from this simple example and we read in the newspapers about neural networks that can classify handwriting or can look at people's faces and recognize who they are, yes, those things are a little bit more sophisticated than this, but in essence, the ideas are not that different from what we're doing here. So if we had a trained machine which had worked out what the right slope was, we could then show it a bug that we didn't know what it was, and it could tell us, actually, it's on that side of the line, so it must be a caterpillar because it's thin and long. What we did there was we learned from data. We trained our little machine by teaching it where that slope, that separating line should be. And this idea of training and learning from data is important. That's how we train almost all of our neural networks and other systems that are machine learning. What we'll do here is have a very, very simple data set with just 2 items in it, just to keep things simple. But in real life, you'll be learning from huge amounts of data. And generally speaking, the more data you have, the better your training generally. So we're coming with the truth, and the truth is that the first bug, which is 3 wide and 1 long, is a ladybird, and the other one is 1 wide and 3 long, and that's a caterpillar. And we know that, and we're going to teach this machine based on that data. There it is on the picture. And just like our first example with the kilometers and miles, we don't know where to start, so we'll just have a random parameter, a random slope there. Well, that's not a good separator because it doesn't separate those two types of bug. What do we want to do? Well, we want to shift it up a bit, don't we? If we look at the first example, which is this one, the green dot, we want the line to be just on the other side of it so it separates the two kinds of bug. So without getting into the mathematics, we're shifting that line up to be on the other side. So we've learned from that first example that our separator should be on the other side of that. And so far, then that becomes a successful machine that can separate those two classes. Okay. And then we look at our second example, and we know that a line should be on this side of it, again, to maintain that separation. So all we've done here is exactly what we did right at the start. We're adjusting a parameter based on what we know the data to be. If this sounds really simple, that's good, because what I'm trying to portray to you is that a lot of machine learning, the underlying ideas really are simple. Yes, they can get sophisticated, but the core ideas are the same. And if you are interested in a little bit of the maths, it's really simple. It's the kind of stuff that people do at school. But there's a problem there. If anyone spotted it, I won't ask. What we've done with that scheme is we've looked at an example, adjusted our machine, and then looked at the next example and adjusted our machine, and disregarded what we learned from the first one. We don't want to do that. If we've made the effort to collect a data set of, say, 10 points, 100 points, 1,000,000 points, if we did that, we wouldn't be learning from the previous examples. We'd just be throwing away what we'd learned. That's a problem. One way to deal with that is to say, as we adjust the line, as we adjust our parameter, we're not going to do it to the extent the math tells us. We're going to ease off the enthusiasm a little bit. So if my math says jump from here to there, I'm just going to say, do you know what? I know the maths is telling me to jump to there. I'm going to adjust maybe a half of that or a third of that or a tenth of that. If you do that, you're taking into account what many examples are telling you where the line should be. And if I'd run the same examples here, you can see with a learning rate of a half, as in I'm going half the changes that the maths was telling me. So I start here. The second result from learning from the second point isn't quite right. I mean, I should be on the other side of that green dot. But by the next example, I'm actually doing quite well. I'm actually splitting that space in half. So just to illustrate that after many examples, my results are actually quite good. And another benefit of this is that if I've got bad data, I'm not so affected by it. So this idea of a learning rate is important. This is my sneaky way of introducing the idea. It'll come back to us later as well. So if you go away today and have a play with sort of, some of the popular sort of frameworks for machine learning, these are the ideas that are worth keeping in mind, particularly if you're playing and thinking, hang on, why is this not working? Maybe your learning rate's too low or too high. Going back in history a little bit, back in the 60s, I think it was, there was initial kind of wave of research and funding into perceptrons and neurons, these little machines. There's a lot of excitement. I'm just going to take you through a little bit of a thought process where we hit a barrier, which resulted in actually people kind of losing interest until a new breakthrough came. So just hang with me a little bit. So we've done the kilometers to miles example, which is very simple. We've done this example with caterpillars and ladybirds, which is a little bit more interesting. Imagine we're looking at data which is created in nature in some way, but depends on a more sophisticated process. So let's, for example, I'm measuring whether I can have ice cream or whether plants are growing. Plants will grow if there's sunlight and rain. Both have to be there. So if I'm taking data about plant growth, I might want to learn how that depends on two other parameters. And you can see there's sort of a logical construct there. If I've eaten my vegetables and I'm hungry, then I can have my ice cream. That's an and relationship. If it's the weekend or I'm on annual leave, then I can go to the park. And either of those two could be true. And if I'm observing whether I'm going to the park, I might find that actually there's a relationship there. Can I teach these machines to predict and model that behavior? This is just saying that actually our machine, our scheme, can take more than one input. And the answer is yes. Because if we model our data with, say, just ones and zeros, if it's on or off, if it's raining or not, if the sun's shining or not, if I've eaten my greens or not, I can use that very simple gradient again to separate the two types of answer I'm looking for. So in the first one, if I've had my greens, so if it's raining, if it's been raining and it's sunshine, then the plant will grow. So that's an and. If there's any other combination where it's not sunshining or not raining, the plants don't grow. But the point of this diagram is to say, even with that really simple machine that we made, which just has one parameter for a line, we can use those to learn data, which is a little bit more interesting. But if we have data that is generated, created by a natural process perhaps, where the contributing factors can't both be true, an XOR relationship, if you know what that is, can we have some combination of this line that correctly separates the two classes? Can we do that? The answer is no. And back in the days of history, this problem seemed to mark the end of that particular line of research into perceptrons, those little machines that we talked about. And there was the AI winter. Oh well. Actually, this problem leads us to a solution. The answer is that we have two lines. Why did I take you through this little journey? Two lines means two little machines working together. And if you know a little bit about neural networks, they are networks of little nodes. And that was the reason why we arrived at lots of little simple nodes working together, because one node has limits to what it can model. But putting lots of them together, we can model and learn the shape of different kinds of more interesting data. So that's the reason why we have networks of very simple nodes. Let's take a little sidestep for a moment. I started off with this question about how my daughter or myself can look at a picture and my brain can see faces very easily. So there's something about the way biological brains work that we haven't been able to quite capture with JavaScript and Python and C and so on. There's some way of computing that's rather efficient at the kinds of tasks that we would like to solve. So historically, AI researchers have tried to understand how nature works, how natural brains work, and taking what they can learn from biology, from neuroscience, and seeing if that can help us make better computer programs. So we know, I mean, this is a really kind of, it's a field where we still have a lot more to learn. We generally don't know how the brain works. We know a bit, but not enough really. But we do know that almost all animals have a basic unit of computation, as it were, a neuron, whether it's a snail or whether it's a human. And those things kind of pass messages from one end to the other, and there are networks of those which connects with this idea of lots of these little things working together to solve more complicated problems. And just kind of just to put things in perspective, we've got these machines. This one's got, 16 gigabytes of RAM. I can get a cloud machine with, hundreds of gigabytes of RAM and terabytes of storage and so on. But then we look at a pigeon. Now, a pigeon has brain, which is about 0.4 grams, and it can fly, which is not a trivial task. fourth order dynamics, I think it is. It can eat, it can navigate, it can fight maybe, it can communicate, it can play. It can do quite a lot with that 0.4 grams of brain. So it's doing something that we should try and kind of replicate if we can. You know, a snail, this particular species, not cartoon species, has 11,000 neurons. Now, if I represented a neuron in, say, 2 bytes, 5 bytes, 8 bytes, 10 bytes, that's teeny compared to the amount of memory in these laptops. That worm there can live a fairly happy life doing some interesting things. It's got 302 neurons, that species. So they're doing something that we really kind of want to learn from. And just a little bit of a real kind of putting things into perspective. That there's a species of whale that has 37 billion neurons, and I think, I might be wrong, I think humans have 20 billion. So it's definitely doing more thinking than we are. And if it wasn't, they would have evolved away. Yeah, so that's an interesting thought. So these neurons in animals, what we've observed is that they do trigger and pass a little electrical signals from one end to the other, and they form networks. But they don't do it straight away. They kind of hold back until the pressure on the input signal is high enough. There's a threshold almost. And we can model that in a computer. You know, we've got mathematical functions like a step function. Lots of nature doesn't work as a step. You know, things in nature are round and soft rather than hard-edged. So we can have S-shaped functions. That happens to be called a sigmoid function. That's quite a popular one that's used in simple neural networks. There are other ones that you can use as well. There they are, passing messages to each other. And that's how we arrive at the architecture of a neural network. You know, it's worth understanding where the history of that thing comes from. There's lots of these very simple machines. Individually, they all do very simple things. And they connect to each other and pass signals. So instead of training just one, we want to train this whole ensemble, this network of nodes, a neural network. Pause. What time is it? Cool. Okay, that looks complicated, but I'm not going to talk about all those symbols. With our very first example, where we converted kilometers to miles, what was doing the learning? We had a parameter, a factor that we multiplied, and we tweaked it to see if we can get a better answer. That's the thing that's doing the learning. What's doing the learning in this neural network? Well, actually, we have some options. Those nodes, remember they had a threshold before they passed the kind of signal through? That could be tweaked. So as we train this network, maybe we could tweak that in response to the error that we see. But actually, history took a different course. And historically, what we've chosen to do is to train the strength of the links between these nodes. So there might be a full link which says, I've got a signal here, and I might amplify it actually, or I might make it smaller. And those weights, those kinds of connection strengths, that is what we are tweaking. So stepping back again from this complicated picture, we want to train this thing. We're giving it examples. We're looking at what the answer is at the end. We say, you're not quite right. You know, there's an error. Let's tweak something to see if we can improve it. And that's what we tweak. It's the weights, the connections between those nodes. So when you go away and look at, you know, really interesting networks, or the kinds of things you read about in the press and in the news, these ideas still apply. Yes, they are more sophisticated, but the core are these same ideas. Afterwards, you can go through and see you know, some of those calculations where you've got an input signal, say a half, multiply it by 0.8, contributes that way. But actually, you've got an incoming signal from the top left to the bottom right as well, so you sum them up. If you're interested, you can see how the maths works. Here's another little interesting point. If I write out with a pen and paper what the signal is as a combination of all these incoming signals multiplied by the weights, and you add them all up, what we find is that it's a big and horrible expression. But if you remember matrices from school, you can actually concisely write what's happening in those neural networks in a very simple, concise form. So the signal that's kind of propagating through is the weight times the incoming signal. Don't need to know that, but if you know a little bit about maths, that can be interesting. And why is this interesting? Two reasons. One, this is general. I can have very large networks and still write it in that really simple way. But apart from saving my kind of pen ink, the second important reason why that's important is computers, particularly if you've got graphics cards, can accelerate those calculations. You can see if I have a big network, there's a lot of that calculation going on. If I've got a computer with a GPU, I can take advantage of that special hardware in there and accelerate that calculation. And that's what's happening when you read about, hardware accelerated machine learning. You buy these really expensive cards from NVIDIA with CUDA frameworks. Essentially, that's what they're doing. They're accelerating that calculation. I'll skip through these slides, but the point here is that as we learn from the error and try to tweak parameters inside the network, if we write out again what that calculation is, and we have a huge page of symbols, we can again write it in a very simple form using matrices, and again, we can accelerate those matrix computations with our computers. So that's nice. Using a neural network and training it both can be accelerated by hardware. One more mathematical idea, just one, and then we'll have some fun. So that's the output at one of the nodes on the network. Those W's are the weights. We're summing them up, we're combining them, we're applying that threshold function. That's horrible. Yeah. I wouldn't want to kind of turn that inside out. Because what we want to do is we want to learn what those weights should be in response to what the error is at the end. If my network is telling me the answer is 5, but it should be 4, that's an error of 1. I need to tweak something in that network to get the answer a little bit closer to what I want it to be. So let's step away, and this is another important idea to understand, even if you don't kind of get into the maths of it, because it'll guide you as you use these kind of frameworks yourselves, because there's dangers there that you need to be aware of. I've got this horrible mathematical expression, and I don't really know how to understand it all globally. Imagine I've got a parallel situation where I'm stuck in this horrible landscape which has got valleys and peaks and troughs, and it's dark, symbolizing the fact that I can't understand it all in one go. How do I get to the bottom safely? I've got a torch. Well, one answer is I look at where I am, where my feet are, I shine the torch down, and where there's a slope going downwards, I move in that direction and try again. And you can see by following this iterative, repetitive process, I can find my way down to a safe point at the bottom without having a full map of the entire kind of mathematical landscape. That idea, gradient descent, you'll hear that a lot if you get into machine learning neural networks. That's the almost good enough, often when we can't solve mathematical problems perfectly, we solve them in ways which are good enough. And this is a good enough way of getting down that hill. It's a gradient descent. And that's what we do with training neural networks. We don't try to solve analytically that mathematical puzzle. We say, okay, let's nudge our way down. Some of you will say, aha, problem, Tariq. What if you ended up in that little valley, that dip there? You wouldn't actually end up with the best answer. You wouldn't end up right at the bottom. Yes, and that's one of the reasons I'm showing you this, because when you go away and you kind of have an experiment with some of those machine learning frameworks, you'll find that they don't always work, and they get trapped in the wrong answer. And this is why they get stuck in the wrong minimum, as it were. You can see here the idea again. We want to get to the bottom of that expression. This is a really simple expression, quadratic one, but imagine it's a really complicated one. We'd work out the gradient at a point, and we'd kind of move in the direction that the slope was pointing us to, and eventually we get to the bottom. Do you remember that thing we talked about learning rates and not jumping so enthusiastically? What if we had a big learning rate? You can see that we might jump over backwards and forwards over the actual answer. We'd jump from one side to the other, to the other, to the other. And that can happen in real life when we're doing this in our day jobs or in our kind of experiments. So the idea of understanding a learning rate is important again. If we turn that down, that parameter, and calm our kind of descent down a little bit, we can get to the bottom, maybe just a little bit slower. So these ideas, I'm explaining them in plain English, hopefully, they're pervasive through all of machine learning, and I hope that you'll find those useful. That's not that hard. Okay, I'll stop with the maths there. I'll talk a little bit about code, not a lot, and then we'll do a live demo. So if you wanted to make your own neural network for fun, because it's an educational thing to do, it's not that hard. Yes, you should go and use things like TensorFlow and PyTorch, which is even more open source, and so on, and Keras, and they're all great things to do. But if you have a go yourself, you'll learn a lot, and you'll learn when things don't work. And that's a useful lesson to have when you go and do it sort of industrially. So I'm going to show you that you probably only need sort of 30, 40 lines of code to do something useful with neural networks. So let's think about it conceptually. A neural network, we need to kind of initialize it, tell it what size to be. We need to kind of be able to train this thing and then query it, ask it a question, get an answer. I've got some code online. It's on GitHub. And there's a blog that talks about this stuff. There's some links at the end, so you can have a go yourselves. And I've written it so that it's not the best code, but hopefully it's the most illustrative code. Really, there's more comments than code. Yes, that looks complicated, but if you ignore the comments, what are we doing? We're setting the number of nodes. This one just happens to have 3 layers. And we're setting a learning rate, and we just have an activation function, and we've chosen that S-shaped one. That's it. That's just the initialization of our neural network. 1, 2, 3, 4, 5, 6, less than 10 lines of code. Let's look at the query where we propagate a signal through, exactly the same as we did with that example of kilometers and miles. We've got a query method. We're taking some inputs. We're applying that matrix multiplication to get to the middle layer of this 3-layer network, and then we're doing it again. So we combine all the weights, and then we apply that kind of threshold function, and then we've got an answer. Simple as that. 1, 2, 3, 4, 5, with 6, 7 lines of code. It really is that simple. And if we're training, it looks more complicated, but the top half is exactly the same as what we just had. We're propagating the signal forward, and then we're working out the error, target, what it should be, minus what we got. That's the error. And then we're doing that simple matrix multiplication again to adjust those weights. Easy peasy. It really is. Okay. The point of showing you that was it doesn't have to be complicated. And you could probably spend half an hour looking at that code and thinking, yeah, I understand that. I can get that. And because it's Python, it's really easy to understand, even if you don't do Python. Okay, so let's look at an actual challenge. There's a set of challenges in this machine learning community which are kind of canonical, everyone knows about them, and they're useful for comparing how our methods work. There's a very famous one called the MNIST challenge. It's about recognizing handwritten numbers. It's an interesting task. These aren't printed kind of Arial or Times Roman. These are people in a rush writing numbers. So is that a 9 or a 4? Is that a 9 or a 4? It's not so easy. This one's rotated. So if we can teach our neural network to look at these pictures and say, aha, that is a 4, that would be interesting. That would be a meaty kind of example. And to do this, I'm using nothing more complicated than that 30, 40 lines of code. You can download the data sets, and they're all kind of, really easy to use, just numbers. And you'll find, actually, I'm skipping forward a little bit because of time, you'll find that you get really good results on the first attempt with, not much kind of like refinement. You could easily, as a first timer, get 70, 80% accuracy. The training set is about, 60,000 examples to learn from, and then you test on another 10,000. So you get 70, 80% of that 10,000 right with a machine that's got just the ideas we talked about, nothing more complicated, honestly, nothing more complicated. And you can tweak you can optimize it a little bit to push the success rate up. You could say, I'm going to make my network bigger, more nodes. Perhaps more nodes can learn more than just a few nodes. And you can see here the number of hidden nodes goes up, and the success rate does increase, but then doesn't increase. And that tells you that what you're doing there is you've reached the limit of the right number of nodes to solve this problem. Any more, you're just wasting computation. So if you're doing this for real, in real tasks, that's an experiment you need to do. You need to work out what the sweet spot is. Any more, let's just throw a big network at this. You're wasting time and computation. Do you remember that learning rate we talked about? If it's too low, you're not going to get great results because it takes a long time to learn. Push it up a bit, and yes, your results improve. Do it too much, and they degrade. Do you remember why? Because you're jumping over that minimum. You're jumping over that kind of sweet spot. You're bouncing backwards and forwards. That's why I raised that example, to explain what you might see when you go and play with machine learning frameworks. And this is a really important point that I deliberately left in. It looks like a messy graph. But the point here is that that's not a nice kind of curve. There's something anomalous going on there. And that's an important point. The way we train neural networks, remember we start off with a random set of parameters, just like we started off with a random factor for converting miles to kilometers. If it's random, from that initial state, it could go anywhere. So some of your journeys as you train these networks will end up somewhere not quite great. It's a random learning process. So the right answer is that you should do this many times and combine your results or take the best in some way. So that's a lesson to be taken away, that just downloading the software, clicking train, typing run, that isn't enough. And if you're a professional in this field, you'll know that only 20% of your time is done, spent on cool things like machine learning. 80% of your time is on cleaning the data, working with the data, understanding your data. And this illustrates the point. If we understand what our data is, our data was numbers. We know that if we rotate them, they're still valid numbers. So why don't we take a number, rotate it each way, and generate new data, still valid. We've just created more training data, and you can push your success rate up to 98%. Now that 98% is really up there with the league tables of academia. I mean, was it last week a paper was published and they had like 99.7%? So 98% with 20 lines of code and nothing more complicated than the ideas I've already talked about, that's not bad. Have a go yourself. It's not that hard. Okay, I'm going to do a live demo, but if you want to kind of find out more, there's a book, there's a blog which people ask questions and I answer them, and there's guest posts on there as well. There's a link to the slides. I've tweeted it as well, so you can always see this. And just to prove you don't need spend £15,000 on an NVIDIA kind of machine accelerator. This is a Raspberry Pi Zero. That's the version that's that big. Costs about £4 or £5, and all this stuff has been. I proved that you could do it on one of those things. So just to kind of prove that. I'm just started. I'm hoping to start. Hoping to have a meetup group, Data Science Cornwall. If you're interested, search for that on Meetup or Google it. And we hope to have kind of regular gatherings where we kind of talk about the ethics of machine learning, AI, tutorials, talks, hands-on kind of hackathons. But the focus of this group will be beginner-friendly. I know some meetups can get really kind of cliquey and specialized. So if you're interested, do join. Okay, I've got 2 minutes to do a live demo. So I've got a trained, so here's one I did earlier. I just wrote a 6, and then I kind of ran it through that code, which is online. And it said, network says 6. Now what I'm going to do is get somebody in the audience to pick a number. So pick a number between 0 and 9, including 0 and 9. What was that? 7, okay. Let's try it, 7. And I'm going to just make that the right size. And save it. And if this says 7, I'll be happy. And if it doesn't, I'll blame the weather. 3, 2, 1, go. Yes, network says 7. So it recognized that was a 7 based on having learned from that set. Anyone else want to have a go? Actually, do you know what? Another good experiment, this touches on another reason why neural approaches are really good, is that, and they mimic what biological brains do, is they're really good when they're damaged. So if I look at you, I can see you, but if my vision is partially, obscured, I can still work out that it's you. If someone whacks me over the head and I have brain damage, it takes a lot of brain damage before that function is impaired. So what I'm going to do is see if I can damage that 7. Oops. How do I turn that around? I'm going to draw little holes in it. Polka dot 7. And save that again. And see if it still recognizes it. So this is an experiment. This is a damaged network. Yep, still says 7. Yep. That just illustrates that neural networks, because they are not relying on one path to get the answer, but a combination of many, you can damage them a little bit or give them imperfect data. So thanks for raising that. That's another learning point. I'll stop there. Thank you very much. Cheers. Hope you enjoyed that.